Hello. So for this video, we're going to be talking about the speed of light. Alright, so in a vacuum, there is nothing that impedes light to travel. So it travels at its maximum speed. The maximum speed of light is 299,792,458 meters per second. But for us engineers, it is 3 times 10 to the 8 meters per second. Or in calculator, it's 3e8. Alright? This is, of course, sacrilegious because it's higher than the actual speed of light, but it's good enough for calculation, I guess. But when a light encounters an atom, there are electrons surrounding it. So, when a photon hits an electron, it pushes the electron to a higher energy state. Alright? And when the electron goes back to a lower energy state, it releases a photon. Okay? So a photon is just energy. And then it releases that energy. And that's how a photon gets slowed down by particles. How much of that light gets released after this absorbed is how transparent an object is. Alright. So, for any material, we are looking at its dielectric constant or the permittivity constant. This is the permittivity of free space, which is vacuum, is 8.854 times 10 to the negative 12 and some units. That is the permittivity of free space, that is vacuum. Alright? But in not free space, for example, air, there are particles in there and the permittivity varies. And actually, the permittivity of this is given by its relative permittivity multiplied by the absolute permittivity of free space. This is the thing that we want. Why? Because with this number right here, with this constant, the permittivity factor, we can figure out how fast light goes through a medium. Alright? Because the velocity of propagation is equal to the speed of light times some factor Vf, which is the velocity factor. Right? The velocity factor is now given as 1 over square root of the permittivity factor or the permittivity constant. Alright? So the velocity of propagation can be simplified to c over square root of ER. So that is the permittivity. The relation of permittivity with the speed of light. Alright. So now let's go to another concept, which is also relevant to light. Now, a light is a wave and a particle at the same time. We just have to worry about its wave properties for now. Right? So, since it is a wave, we can have its wavelength. Alright? The wavelength of a certain wave is given by lambda, which is equal to velocity of propagation over frequency. For light speed or for vacuum, the velocity of propagation is c. But we know from the previous formula this is c over square root of ER. So now when we want to find the wavelength of light in a vacuum, we have to find its epsilon r, or the permittivity constant. And then we divide by the frequency of that wave. Okay. Now, in the real world, we have physical lengths. The physical length is measured in meters. For example, something is 5 meters. Alright? But in transmission lines, in the study of transmission lines, we have something called an electrical length. And this is essentially the same as physical length, but instead of meters, it's measured in how many wavelengths there are. So for example, this is 0.5 lambdas. meaning that this length is equal to 0.5 times the wavelength of the speed of light that's traversing through it. Alright? So, if the speed of light, if 0.5 lambdas is given to be 5 meters, then we know that lambda is 10 meters. Now from here, we can, if we know ER, we can get the we can get the frequency of, well, if we have the ER, we can get the frequency of the light going through that line. Because we know lambda is equal to Vp over F. And Vp is C over square root of ER. Alright. And we can rearrange this to get this. Alright? And there we go. We have the frequency here, we just need ER, and C is a constant, and we can get the frequency of this. Given that ER is 1, so that's just, what is that? That is free space. We can eliminate the ER term altogether. We get C over F. Alright. Let me just rearrange this. Alright. So in order to get frequency, we can rearrange it together. We get C over 10 meters. What is C again? That is 3 times 10 to the 8 meters per second over 10 meters. We get 3 times 10 to the 7, which is 30, and then megahertz. That's the frequency of the light traveling through a vacuum with 10 meter wavelength. Alright? And that's it.